You guys ready? You guys ready? Bring it around, bring it around. A couple things. Adam, that's our contact from Missoula Concrete, emailed me this morning and said, hey, we'll be in Missoula on Friday. Will that work for your class? And I responded, by Missoula, do you mean Bozeman? Because you are Missoula Concrete. I feel like you're always in Missoula, unless he's from, right? You know what I'm saying? Unless he's not there and he's coming. I don't know, but he's I don't know. So I emailed him back and I said, if by Missoula you mean Bozeman, that'll work out perfect. And then we'll see what he does. So again, by the end of the day, team captains, email me with all of your questions, right, that you think you might come up with. Just so what you need to get started. Obviously, there's going to be some other questions that come up along the way, but just to get started. Okay. And that's it. Okay. So we have a couple more topics left. So we're on deflections, right? We talked about immediate deflections last time and how you predict the immediate deflections. One way of doing it, right, is to pretend that the internal moments are an equivalent external load. And we use, for example, this harped section, right, where the one depression point in the middle is going to cause a moment that looks like this. An equivalent force that gives you the same moment would be, just a point load in the middle going up like that. And this is what its moment would be. And then you just, go through the equivalent forces and you can determine what that is. And just follow that process that we did. Or you use Stan's method down below here, which, I don't know where he came up with it, but he came up with it. But it's just a way of doing it. But it's probably based off of that equivalent force. And we applied it there, okay? You're going to have to do this in your next homework. We're going to have to predict deflections, okay? And that was immediate deflections. And we briefly talked about immediate deflections under cracked beams. We're not going to do this. But if for some reason you had a class C or a class T beam where you have some cracks that are forming and you're trying to predict the deflections, you could use the bilinear method where you assume deflections with an EI up until cracking and then a reduced EI after cracking, or you could cut the corner with this EI effective, which I think you did in Tim's class. Okay, now we're on to long-term deflections, right? This is all immediate, right? But over time, there's going to be creep and shrinkage and all these other things that are at play, and we have to account for those things. So I just got a bunch of notes to write in here. That was my keyboard open so I could really fly. Right. I'm sure you appreciate that, right? Creep can cause, just to show you the complexity of what's happening, or downward deflections, shrinkage, are those bad for you? Are those bad for you, Luke?
Probably.
But it's better than chew.
Yeah.
Correct?
Yeah.
Does it cause cancer? Does nicotine itself cause cancer, or is it the tobacco that causes cancer?
They haven't proven that it does.
Pending case study. All right.
Generally, I'll let you know in
30 to 40 years if you get that. Is that a thing? How many people do that? The Zins. Okay. Users. Not you, Kira. You're not.
Zin Galley.
Not at all. All right. You know what was a big thing when I was in high school was snuff.
What?
Do you know what I'm talking about? You know what I'm talking about? Where you snort powdered tobacco up your nose. That was hell in the capital in the 90s. That's what you do. You gotta be cool. And then all the guys walk around, and then you got a chew can spot in your back pocket. Man, that was cool. I didn't do that. I never chewed because my brother, when I was 7 years old, gave me a chew. And I got violently sick, and then since to this day I cannot. It was a good move on his. I don't think that's the reason he gave me the chew, but
He was looking out for you.
he was looking for. He's like, I'm gonna make him hate this. Relaxation in steel causes downward deflections. I'm just painting a picture. There's lots of stuff going on. All right, Young's modulus. Modulus changes with time. time. And as concrete strength changes, and it's all tied to that. Young's modulus is a function of the concrete strength, and so if the concrete, if you're going from 7 days to 28 days, right, there's going to be a change in the elastic modulus that's happening, and then even over time, concrete continues to gain strength throughout the lifespan of it. It's tied to pre-stress losses. Right? Pre-stressing forces change. That's happening, right? While if my pre-stressing forces are changing, then my deflections are going to change, right? And that's happening throughout all this, and they're really intermingled, and trying to pull them apart from each other is hard, right? And so then I also have this written down here. I have crapshoot. And then we had a big discussion last time, and we might as well have the discussion now. Or is it crapshoot?
It's that one.
It's not that one. It's crapshoot for the game. Craps.
Shooting crap.
Shooting craps. It's luck of the draw. But then this is also fitting. The crap shoot. That's where the poop goes, is the crap shoot. But then also somebody last time mistook this for trap shoot, which is also something completely different. Because they were like, oh, isn't that where you shoot clay pigeons? I was like, no, that's trap shoot, not crab shoot. Okay? We got this. But the point is, it's a big guessing game. It's a big guessing game. Right? It's a big guessing game. Okay, the code does try to approach this, right? And let's go through the codes. Code approaches. We saw what ACI did, right? We a few weeks ago, or a week ago when we first brought this up, we saw what it did. ACI says these are important and you should account for them. And that's the only guidance it gives, right? And then, except for it provides some references. Right? There's a couple of them out there, right? And some of them are back to the 60s and stuff, and they're still applied. I would guess, we're gonna pick one, the easiest one to use. If we're gonna use the PCI has this multiplier method. We'll get to that in a second, but we're going to use that one just because it's easiest. In the real world, you're going to probably use a computer program, and then built into it's going to have something. I was talking to someone the other day that was using, the other day meaning 2 to 3 years ago, they were using a program, and I was like, how do you account for your long-term deflections in your estimates? And he goes, oh, I just go over and I hit the I cracked button. And I got scared a little bit, right? Because those are completely different topics, right? There's cracking, which is immediate, that would happen, when you apply the loads, and then there's long term that comes from creep and shrinkage stuff, and they're completely separate. And he was using these. So again, the importance of teaching you this stuff, because so you're not like, oh, I'm just going to blindly use, and I'm just going to use this programming. Like now you'll know what buttons are put to push and what they do, right? At least have that a starting point. Okay. Buttons to push, yeah. AASHTO, it provides more guidance. It has a prescriptive method. Tied closely with losses, and it's empirical. Everything in concrete is empirical. You probably go without saying that. Very little is tied back to actual mechanics, okay? And we're going to use this method in the PCI design manual. This is 5.8.4. And it has multipliers. Multipliers based off of that, and then comes from one of the references. thing is still acting up here. It gets long, it gets delayed. The textbook is on. Okay, so it's based off of that. All right, so let's look what this AC or this PCI method is. Come down here. This comes right out of it. So you have a copy that, this is ACI to begin with. This is what you do if you have regular reinforced concrete, right? And this is, we briefly talked about this before, which we're not going to use this method. This is what you did in regular reinforced concrete. I don't know why I included it here. Put a big X there, right? I'm not, and this doesn't apply here. That's for regular reinforced concrete. I think I just put it in there to show you the use of this. This is the method right here, right? And I'll show you an example in a second, because they also provide an example. The PCI design manual is really good in that regard, because they tell you how to do something and then they give you a nice example afterwards. So at erection, deflection downward component applying to elastic deflection, you get a factor of 1.85. Camber upward component, okay? Welcome, Neil. Welcome. I saw you on TV.
Thanks.
Yeah.
How'd it look out there?
You look good. You look good. You were in a huddle.
Sweet.
What's that?
That Julius.
Oh, that was pretty cool. Yeah, that was pretty cool. That was ESPN top 2. It was number 2, top 10. Yeah. Did you see that? He hurdled the guy. Just a big whiff. That ever happened to you, Neil? You ever get somebody jump you?
No.
Wouldn't that be embarrassing?
I don't know if they try.
Yeah. What are you, 6'3"?
6'3".
Yeah, that'd be a big jump. Jump over. I mean, he was standing straight up, right? He was standing straight up. He jumped right over the top of him. That's gotta be embarrassing. Right, doesn't it? Right? You're like when the guy that Saquon jumped over last year backwards, right? I wanted to see if that guy ever like released a statement about it, and he never did, right? Like I would release it as like, oh, I got screwed there, but instead he kept it inside. He never came out with a statement. And then it's on the cover of the Madden cover. The pinnacle of your career is you tackle Saquon, he's jumping over you backwards, right? Like, that's really unfortunate. Well, I'll show you this place. So if you're calculating direction, at direction you have deflection downward, that gets hit with a factor of 1.85, and then you have a camber upward due to the upward component applied to the elastic camber due to the preset. So the upward component gets hit with a factor of 1.8. And so those are, medium size. At final deflections, right, we have the downward deflection component that gets hit with a factor of 2.7. The camber upward gets hit with a factor of 2.45. The deflection downward gets hit with a factor of 3.0. And then deflection downward caused by the composite topping, which we're getting into composite later. So that hits with 2.3. So it's just very prescriptive how you apply it, right? Example 5.8.4.1 does this for a particular exam or for a particular problem, right? So they go through and they estimate the deflections and they have all the different components, right? They calculated, for the different components, and they make this table. So when you do this for your homework, I would make the same table. So your first thing you do is you calculate the deflections due to the pre-stressing, right? That's going to be an upward deflection due to the pre-stressing. That's calculated up above. So this is at release. And then you have the self-weight of the structure, and that's going to be, of the element, is going to be 3 inches down. And so the total deflection is going to be 1.35 up. So at erection, it's actually going to deflect up 1.35 inches. Because the self-weight kind of pulls some of it out, and the pre-stressing moves up. And there's no factors hit there because that's just immediately. You transfer it, and then it's just going to immediately deflect, okay? Then when we go to at erection, this is like within 28 days or something like that. After it gets cast, they move it to the site, they put it into place and stuff like that. And at that location, so there's time that's passed. And so during that time that's passed, you hit this upward deflection with a factor of 1.8. And so we have 7.83. And then you hit the downward deflection with 1.85. And so you have a total of 5.5 on the downward direction. Then you add those two together. And so at erection, you're going to have a deflection up of 2.28 inches. So it actually, right, it increased. Right? Under the same loads, it increased just because the creeping up is what's happening, right, just over that 28 days, right? Then you apply the superimposed dead load, like the thing in place, and so you get another downward deflection of 0.4, right? And so the total deflection with the superimposed dead load and the self-weight and the pre-stressing of 1.8 at erection. Okay, then we go on to the final state, right? And so then this upward deflection gets hit with a factor of 2.45, so that's going to result in 10.66. Then this one gets hit with a factor of 2.7, and so it's going to be 8.1, and then the total is going to be 2.56. Then we hit this downward to the superimposed dead load, that gets hit with a factor of 3, that's a down 1.44, and so the final camber is 1.12 inches, and then the live load, there is no time dependent component to that, right? Because the live load comes and goes, right? It's the cars driving over it or the people on it and stuff like that. And that doesn't cause like long-term deflections. So you just calculate just the live load and then just add it onto that. So this thing, in its place would have a downward deflection of 1.4. So you're going to do this as one of your homeworks, right? Actually, your next homework assignment, did I bump it all the way to Wednesday? Yeah. Wow, what a softie, right? So the next one is you're going to open up that same PCI design manual, which you're learning how to read and stuff, and you're going to make sure that their loads work for every single case. You're going to take that load that says safe superimposed live load, and then that's going to be your demand, and you're going to make sure that it works for your service cases, your elastic service cases. You're going to make sure that it works for your ultimate moment. You're going to make sure that it works for your shear capacity. You're going to estimate its pre-stress losses, which we're going to get to that in a little bit, and we're going to estimate its deflections. Because I don't know if you saw that in the table. It did have deflections estimates, and you should get pretty dang close to what they have in that table, because we're going to use the same methods that they have. It's pretty fun. And what's good news, right, is you have all the programs to do that at this point, right? You have the elastic analysis, you have the shear capacity, what you will by Wednesday. You hopefully will have the shear capacity, and then you also have the ultimate moment capacity all built into it. And you can see that actually and then you'll be able to see which load case actually controls. There's one of the load cases that you see that's where it's right up at it, right up at the limit.
Is there a 2 multiplier for dead load? Here.
Yeah. 3. Oh, yeah. Actually, this is a good point. I misspoke. It's 3 times 2, and this is 2.45 times 1, and this is 2.7 times 1.
Where do 1 and 2s come from?
So at release. So these two multipliers get applied to the at release conditions, right? So they don't get applied. I misspoke. I said they got applied by the. And that's obviously not the case. It does not get applied. You don't apply it to the erection case. You apply it to the release case, because 2.45 times 7.83 is not 10.66. I don't have a calculator with me, but I'm pretty sure that that's the case. So I did misspeak. So this is 2.4. So it's all based off of these two are released off the release, and this one's released off the erection. What's that?
It's telling you what step you're multiplying.
Yes. Yeah. This.
A number.
Yeah. Yes. Correct. Yeah. Exactly. It's which column you're multiplying it by. By the way, I'm really proud of myself that I said erection like 100 times, and I didn't crack a smile or anything. I just want to say I'm growing up. In my mind, though, I'm just like, oh man, this is funny. Okay. It's a childish thing. I tried my best. I did it. I'm really proud of myself, but I couldn't hold it in. Okay. It's just funny. Just funny that it gets used there. Okay. Any questions about that, right? You'll dive in. You'll see it's pretty straightforward, right? And then they literally have this example from start to finish, and you can follow it. Okay. All right. Pre-stress losses. All right. This again is just a crapshoot. We don't know how to do this, right? It's concrete. It's time dependent. We're guessing as well, right? Another crapshoot. Right? But what we got to do is we got to go FPJ, right? Because that's how much we've actually, that's what we've jacked our tendons up to, okay? And that's going to go from FPJ to FPI, right? Because there's losses that happen between FPJ and FPI, okay? FPI, and then that's going to go then to FPE. Right? What are we actually going to use? What is our effective pre-stressing forces as we go? And there's the steps to do that, right? And there's methods for doing that. PCI chapter 5.7 is where this is at. Also, we have ACI. We're going to use the PCI method. ACI has a method too. ACI 20.3.2.6. And by saying it has a method, it doesn't. It just it says these are important. You should account for them. Here's a reference, just like they did in the deflections. ACI does put out a 432R16. So that's committee 432R16, and they have, this is all on pre-stress losses. Right? It's a couple hundred pages long talking about estimating that. And so if you really do find yourself doing this, estimating pre-stress losses, that's a really good reference, is going to that committee. There's a committee strictly for that. AASHTO has a nice method too. We're kind of beating the horse to death on why you get those losses, but we're going to keep beating the horse to death. So this comes out of Stanton's notes. He's got a nice little section on pre-stress losses. That's another thing, by the way. Keep on keeping on, right? You keep reading the Stanton stuff. That's a lot of my notes are pulled directly out of that, and then you should be able to see some of the stuff I've skipped over. Some like Stanton's shear chapter. He spends a lot of time deriving VCI and VC. Look at Connor read VCI and VCW. You don't have to do that, right? Because we just jumped right to what the code says. But he spends a lot of time deriving. Don't look at that. But then some of his commentary on this other stuff is really spot on. No, do look at Stanton, but with the appropriate amount of detail, right? Like don't dive in too deep, but then kind of like skim it in certain areas, but then really dive in some other areas, Connor. This is a good point. He has this nice discussion, right? So this is causes of pre-stress losses, right? And then he's kind of tried to quantify them in this very sophisticated table, right? So this is the event, and you got some stuff coming from concrete, you have some coming from the steel, and then it's going to be different for pre-tension and post-tensioning. They're going to be different, right? For instance, thermal during casting, that's going to affect pre-tensioning, but it's not going to affect post-tensioning, because post-tensioning, it's come to strength, and then you apply loads and stuff like that, okay? Elastic shortening, right? Big deal here, not at all in post-tension. What elastic shortening is, right, is you stretch your steel, cast your concrete, wait for your concrete to come to strength, and then go slice it, and then it transfers the load from from the steel into the concrete. That when it shrinks, right, when it squishes the thing, you're gonna get pre-stress losses immediately, right? Immediate. And that's gonna be a big deal in pre-tensioning. In post-tensioning, it's not at all, because again, in post-tensioning, your concretes come to strength, you put an anchor on one end and a jack on the other end, and you just crank, and then while you're cranking it, it's squishing it while you're cranking it, right? And so then it just gets shorter, and then you put the anchor on the other end, and then it's already worked out the losses there, right? It's already squished it, and it's being accounted for when we're pulling on it, okay? Shrinkage affects both of them equally, right? Because that's just, as time goes on, concrete will shrink over time, right? Because it dries out, basically, right? And then there's also chemical reactions that are taking place, and those chemical reactions end up with a smaller volume afterwards, and so they're equal, but they're not as big as this elastic shortening. The biggest player in both of these things is creep, right? Creep affects both of these things significantly, right? So this is just as under sustained load, it's like glacier flow, the concrete just shrinks over time or squishes over time, and then your pre-stress losses then go down, right? And then that's, this creep is that's why we have to use 270 KSI. I mean, all of these things is why we have to use 270 KSI steel, because all of these things are quite significant when you transform out. But if you start out with 270, then it gives you a lot more wiggle room. Friction losses, right? That's a big deal. And so what that has to do with, we'll look at this. I don't have it in here. I'll bring it from my other notes. But, if you have, right, if this only affects you, right, in post-tensioning, right? Because in here I'm pulling this way, right? And I'm pulling this way. Oh my gosh. Okay, and pulling both directions like that. And then, or actually, what you're actually doing is you're fixing one end, right? There's an anchor on this end, right? And I'm pulling on that. And then you can see, right, there's gonna be friction as it goes around that corner, right? You're pulling on it, and it'll be, it's trying to straighten out, and it's dragging along this thing as you go around that corner. So that's a friction loss. So what you pull here, right? What you pull here isn't what the actual stress is throughout this whole entire thing, because you've wasted some of that on the friction that's going there, right? And so that shows up under post-tensioning, but not in pre-tensioning, because even if we do a harp section, right, it's already stretched, and then we cast the concrete around it, and then we release it, and so there's no friction. You're not pulling against like a fixed concrete at all. It's just there. Yep. And so it's not there. Anchorage slip, right? There is no such thing as, there is no anchors in bonded, right? Because it's just attached to the concrete and they move together. But then there is, obviously this would be a big deal. If your anchor fails, or if there's a little bit of slippage that happens there, then you're going to get pre-stress losses, right? If it slides a little bit. I keep meaning to bring in one of those. I have one sitting on my desk. I did bring it in. Did I bring it in? Did I bring in a strand? I didn't bring in a strand. I did bring one in. Yeah, because you told me there's only 6. Right, Thomas? You were like, there's only 6. So I was like, I'm pretty sure there's 7. And then we recounted and there's 7. But then I didn't take apart the anchor.
Somebody did.
Somebody did?
Put it back together.
Okay, good. And so inside of it's these little wedges, right? You saw that, right? The little wedges. And so then you apply the load, and then the more you pull on it, the more it squishes down on it and stuff. And so it's how those wedges work. And they do slip sometimes, right? And that's going to be a major component of that. And then the other component is relaxation. So if you just pull, just like creep, it's like kind of it's the steel that's doing this under sustained load that just relaxes. Under sustained load or under a certain distance, it just gets a little bit longer. And I think it has to do with the 7 wires stranded together, and then you just pull them, and then they just kind of like untwist a little bit, and then they just, in the process, just relax it a little bit. And they have low relaxation steel to try to reduce that because it improves the amount of pre-stress force you have. So that's kind of neat. This is for pre-stressing. Just to show you like a timeline. This also came out of Stanton's notes. Right? What does it do versus time? How do my pre-stress losses happen? This up here would be our FPJ, right? And then right down here would be our FPI, and then over here would be my FPE, right? So just immediately, right? Immediately, this is for pre-tensioned members, right? So pre-cast, pre-tension members. You kind of pull it, and while you're holding it in place, you get a little bit of relaxation that happens, right? You start out with 190 KSI, and maybe you get down like 180 or something like that by the time you actually cast the concrete, right? Then this is a vertical jump right here, because that's you cutting them, right? You come in, whooshie, whooshie, slicing them. I'd really like to see him do that. I think you got to do them at the same time on both sides. Yeah, right, you do, right? Because if you don't, you have the other ones attached, but right, you can imagine if you cut one side, not the other side, it's gonna suck it in one direction as opposed to coming in both. And so you could, maybe the last one is the most important, because the last one, it'll actually move, right? So if you're maybe we get to see it. Maybe in Missoula we could go see it, because I'm pretty sure, I think we did a tour of a plant in Billings. Almost died because it's so dangerous over there. We did a tour of the plant over there, and then the university won't let us go there anymore. It's just too dangerous.
Because of the plant.
The town, Billings in general. It's off limits. You just can't go there.
Are you serious?
No, I'm not serious. Yeah, there's a few places banned by the university. Sudan, is that where the pirates at? Where are the pirates? Somalia. We can't go to Somalia or Billings. Those are the 2 places you can't go. The university says no go. Too dangerous. Great Falls is in there too. Great Falls is in there. Billings. Am I serious? They actually are. We do have satellite campuses there. Yeah, but I think when we did tour the plant, we did ask them that, and they have a person on either end, and then they have a schedule. They have a schedule for how they're releasing it. So they're like doing the upper right, then they do the bottom left, and then they actually have like a process that they're going around. And I think they do it with a torch. I don't think they do it with scissors. I always draw it with scissors. It's not scissors. They have a torch at either end. They just release both at the same time. But the point there is it then transfers that immediately, and you get losses immediately because the concrete there just squishes. That's why it's a vertical line, because it's like shrinks up. Okay, and so then that's when we talk about at initial. This is it. It's right here. Right? It's right here. It's after that elastic shortening that we have, and then we have to go from FPI to FPE. It's just a duration, and it's just a slow decrease. And there we have shrinkage, creep, and relaxation that happens in between those things. Okay, and this is assumed to be, just to put things into perspective, that to right. Oh, I'm trying to draw to where that service case is. That is 5 years. Assumed to be about 5 years. So when we say that we are going to use FPE, we do that at 28 days, right? We do that at 28 days. We use concrete compression strength at 28 days, but really when we say give that FPE, it's the 5 year mark that we're aiming for, right? So really when you do your actual construction, you're over here someplace. So you actually haven't had those pre-stress losses. It's just like we designed for that 5 year, and then it just kind of fades away, and then you max out how much pre-stress losses. It won't continue on forever. Actually, I think technically it's asymptotically approaching the thing. And then the reason it's showing the live load going up and down, because that's what's going to happen. Deflections, as you apply load, it's going to stretch it a little bit more, and then as the load goes off, it's going to go back and forth. And so that's just kind of showing that it's kind of tapers off down there. You guys go, you say aunt or aunt? We got, what's the, got any aunts in here? Where are you from? That's okay. One of my sons is an aunt. He says aunt. I don't know how it happened. I failed him as a parent.
Aunt, but aunt if it's right before their name.
Right. That's what he does. But then he slipped the other day and he called my sister Aunt Shelley. Aunt Shelley. It was like, what the fuck? Like, what are you doing? Whose kid are you? Funny, Gavin. Funny, you son of a bitch. Yeah, let me do something. I want to get.
Minus points for Gavin's team.
Yeah, Gavin's out. Gavin's team's out. Gavin's team's getting an F.
So we don't have to do it anymore?
Yeah, but you're getting an F though. You have to do it. You have to do it in a couple years when you take this class again. You don't have this, but I'm gonna. This helps you in no way, but I'm gonna. But I'm gonna put it in. I know. Okay, just to copy that down really quick. I need to transfer that to my skeleton notes. But this came out of a presentation. I don't know where this came from. Actually, to be honest, I don't know where it came from. But this I thought was kind of telling. I think I went to a conference and they had this thing up here. So we have pre-stress losses. We have immediate pre-stress losses and time-dependent losses. We have elastic shortening. That's one of the immediates we talked about. Friction is an immediate loss, right? Because as you're pulling it to tension it, that's going to be immediate loss. And obviously anchorage slip is going to be immediate. So if you get a little slip, then it's like immediate loss. But then the time-dependent are creep, shrinkage, relaxation. So we've discussed that. I don't know if you need to copy those bubbles down. What you could do, you could take a pic. Oh, poor kids can't. But people with tablets, you can take a quick picture of this and then paste the picture into your notes. Or I can post this thing afterwards because or it's not that important. So this came up when at some point soon we're almost. So in terms of topics, we have pre-stress losses. That's what we're doing right now. And then the next topic, the only topic we have left, is composite construction. So that's if you have a pre-stressed beam and then you put onto it a slab on top of it. And it's pretty fun, to be honest. It's pretty fun to deal with because there's a lot, like if you thought the sequencing was a lot before, like with the initial and then the right, you got initial conditions, then you have service conditions, but then now you have a slab on top, and then at some point the slab and the concrete act compositely, so we have to use method to transform sections. I really enjoy it, but so we're gonna do, that's the last topic. Okay, then Kyle, who I can't get a hold of. I can't get a hold. Last I heard, he was in Mexico. He's gonna teach the post-tension floor design section. Okay, and then that's it. And then we have bridges. Then we have 2 weeks of bridges, right? And then you have your project stuff. But anyways, by this time, last time I taught the class, Kyle had already taught a couple classes, and he kept talking about wobble losses, like as if we knew what that was. And so we had to have a quick council afterwards to be like, okay, guys, this is what wobble losses are. I had to look it up. Okay, so this is, I just think it's just cool to call it that. So this is in post tension is what happens. This is the black line right there is what we assume. This is a draped section in a post-tension member. So you have this parabolic thing. That's the assumed. You're obviously going to get friction that we talked about. If I pull on the end of one of these things and anchor the other end, there's going to be friction that happens, between the concrete and this around this side, right? It'll be on this side of it because it'll be trying to pull up and there'll be friction on that side as it tries to go around the corner. What wobble losses are is that, when they actually cast this thing, is it really going to look like that? No, it's going to have little supports along the way, right? And those little supports are going to do this. And then in between the supports, it's going to sag, right? And so this is like on the, I think I showed you axles where they lay it all out on the big floor, and then you try to make it so that it has that, but you only put chairs in certain places, and so that like in between those chairs, it's going to sag in between those chairs. That's what's shown in there. And so then you're going to get this additional friction losses due to those little wobbles that are happening. So you not only do you have it along the whole length, you also have it like in between those chair supports, and which just adds on and complicates things. And so then now when he says it, you'll be able to like, yeah, I get it. I know what that is. Mike taught us about that, right? Friction losses of post-tension concrete members fall into two categories: curvature friction losses and wobble friction losses. Right? And then you talk about that. So I can post this if you want me to post that. Okay. All right, this is great. So estimating losses. Well, what happens if we do it wrong, right? Is it a big deal if we do it wrong? It's a big crapshoot, right? We don't really know. Is it that bad if we mess it up, right? So let's talk about what happens if you mess it up. Let's look at deep. Right? If I underestimate my pre-stress losses, what happens? Right? In this case, you lose more stress than expected. Right? So FPE is less than expected. Which means you might crack under service loads. Because you're designing for a higher FPE, right? This is the elastic side of things. You're designing for a higher FPE, but you're getting a lower FPE. And that can be bad, right? In terms of serviceability, service conditions. Right, cambers, deflections will be off. But here's the kicker here. Most likely will not kill people. Right? Not completely, but most likely it's not going to happen. It's not going to result in someone dying. Right? It's not going to affect our overall load. Right? I mean, it will a little bit. There's a little bit of an effect. Right? Just because you're dealing with your tendons and they're starting at a certain strain and they're going a little bit higher, and now you're off a little bit in that regard. Okay, but most likely they will not kill people. Not safety issue for bonded pre-stressing. can be more of an issue for post engine. See note from ACI. That's a side note too, by the way, right? Like the pre-stress losses isn't just the ultimate moment. It also affects or can affect the shear, right? The shears are dependent upon your pre-stress, like the FPE or whatever variable it was that ACI called it, right? That pre-stressing force, or FSE, I think it was FSE is what they use, right? That pre-stress, if that's less, then your shear capacity goes down. And so it'll affect your shear capacity more than your ultimate moment. But in post-tensioning, there's a little note in ACI, we'll look at it in a second. It's just post-tension, you gotta be a little more careful. It might affect a little bit more.
So that's note, not.
Not a safety.
See not from ACI.
Oh, see. I wasn't done yet. What the fuck is that? Yeah. See not for ACI. Thank you. Okay. I do have some notes in here. We went into a deep dive last time, or several times ago, where we discussed it most likely not kill people unless you I don't know. It was funny at the time. It was fun unless you break bad. Like if you lose your job because you misread your pre-stress losses and then you crack. And I just watched that show, Breaking Bad.
Yeah.
Right? And then it's like you see how every like moral decision you make, you could see yourself making those same moral decisions, right? Like you're like, oh, I guess I could see that. Everybody seen Breaking Bad? Well, you should watch it. It's excellent. It's really good. But the premise behind this, he's a chemistry teacher and he gets cancer and he needs to support his family. And so maybe the very first jump, Kira, maybe the first jump of deciding to make meth. But from there on out, you can see yourself making the same moral decisions that he makes, right? And one of them is like, oh, he needs to supply for his family and stuff like that. So he starts making meth, and then he breaks bad, and then he starts making these terrible moral decisions that end up being, you know. And then the ending was just beautiful. The only part I had a problem with, Kira, is the airplane exploding and then it landing on the house. That's because it was the likelihood of it being the house that he was. That's not a big. This is way. It landed on the same house that he was in. Do you see what I'm saying? Like that was a big jump. He caused the airplane accident, and then it hit the same house that he was in. Like that was just like, oh, okay, well, or with near it or some, you know what I'm saying?
I feel like I just forgot about that.
Yeah, that was the one part I was like, oh, come on. The rest of it though, I'm just like, I didn't ruin anything, Anika. I didn't ruin anything. You go watch it.
Well, luckily I already watched that season, but that's like the whole suspense for that whole season.
Oh yeah. Sorry. I mean, what is it's like
I feel like when
it's
something's
like
a decade old,
it's 15 years old. You should have seen it by now. There's no such thing as a
I'm not gonna watch it when I'm like 8 years old.
yeah. Oh yeah. Good. Hey, fuck you, Anika. Huh? What are you saying, huh? You say making fun of my age? Is that what you're doing?
No,
I would have been 6.
I know. I shouldn't be saying F you to students. I apologize. I was joking. I didn't mean.
That's our future dean right there.
Yeah. No. I tell my wife that I say the F word sometimes. She's like, you do what? And then if I told her that I called Anika a very nice person, a nice young lady, I told her to F off because she said she didn't watch it when she was 8. Like that'd be, again, my apologies, Anika. I shouldn't say that. All right. Okay. Oh yeah, I do have that one note. I just want to add that. Will affect shear capacity. Just so you know, right? Because that FPE will affect shear capacity. And then we'll say use conservative method for predicting losses. You'd rather not underpredict them. But what happens if you overestimate? We'll talk about that next time. Okay. All right. That's good for now. Okay.